Satellite navigation is based on a global network of satellites that transmit radio signals from medium Earth orbit. While many are familiar with the 31 satellites of the United States Global Positioning System, GPS, 3 other major constellations provide similar services like GLONESS, Galileo, and Beidou. Collectively, these systems and their augmentations are known as the Global Navigation Satellite Systems. The basic GPS service offers users approximately 7.0 meter accuracy. 95% of the time anywhere on Earth, this is achieved by each satellite emitting signals that allow receivers to determine their location and time by processing signals from at least 4 satellites. These satellites carry highly accurate atomic clocks, and the time information is embedded in their broadcast codes. Receivers use the time difference between signal transmission and reception to calculate the distance to the satellite. By measuring the ranges to 4 satellites, a receiver can compute its latitude, longitude, and altitude and time, while also accounting for propagation delays caused by the atmosphere. Let's move on now to the history of the satellite navigation systems. The evolution of navigation from using stars to artificial stars represents a major engineering leap, moving from a visual weather-dependent craft to a persistent global utility. The roots, which is the ground-based radio navigation. Before satellites, navigation relied on high-powered land-based radio stations using systems like LORAN, which means long-range navigation, developed during World War II. These systems measured the time difference between signals from fixed towers to determine a position, but were limited by the Earth's curvature and geography. Next is the move to space. In 1960s, the U.S. Navy launched Transit, NNSS, the first operational satellite system, which used the Doppler shift to locate submarines. However, it was slow and required users to wait hours for the satellite to pass. Next is the birth of GPS, started by the U.S. Department of Defense. In 1973, the first Navstar satellite launched in 1978. Originally, the military intentionally degraded signal accuracy for civilians, selective availability, but this was switched off in 2000, leading to the rapid growth of consumer GPS in phones and vehicles. The global expansion. To avoid strategic dependence on a single nation's military, other powers developed their own constellations. The GLONASS from Russia started in the mid-1970s and fully restored in 2011, while Galileo from European Union, a civilian-controlled system designed for high precision, becoming operational in 2016. Beidou from China completed a global constellation in 2020, uniquely featuring a short message service SMS capability.
System architecture. The global navigation satellite system architecture is composed of 3 integrated segments: the space, control, and the segments. The space segments consist of constellation of satellites, typically orbiting in medium Earth orbit at approximately 20,200 kilometers, which act as a precise orbiting vehicles by continuously broadcasting radio signals containing their exact position and time data from onboard atomic clocks. Managing this constellation is the control segment, a global network of ground-based monitor stations and master of control facilities. These segments track the satellite's health, calculate precise orbital paths, and uploads clock corrections to ensure the broadcasting data remains highly accurate. Finally, the user segment includes any device equipped with a GNSS receiver, such as smartphones, vehicle navigation system, or surveying equipment. These receivers capture the signals from multiple satellites simultaneously and use the process of trilateration to calculate the user's three-dimensional position, or the latitude, longitude, and altitude, and highly accurate time. The control segment uses a global network of monitor stations to track the satellite signals as they pass through the Earth's atmosphere. Since the ionosphere and the troposphere contains charged particles and water vapor that slightly slow down radio signals. The control segments calculate this specific delay constant and includes them in the navigation message. This allows the user segments to subtract the atmospheric delay for a more accurate distance calculation. Furthermore, while satellite atomic clocks are incredibly stable, they can still drift by nanoseconds over time. Because light travels at approximately 300,000 km per second, even a 1 microsecond error could result in a position inaccuracy of 300 meters. To prevent this, the master control station compares each satellite's clock against the ground-based master clock. The upload precise clock correction parameters, ensuring the entire constellation remains synchronized to a universal time standard. Signal structure. The signal structure of GNSS, such as GPS, is composed of three essential layers: the carrier frequencies, the ranger codes, and the navigation messages. The carrier frequencies act as the physical transport mechanism, operating within the L-band or 1 to 2 GHz to ensure signals can penetrate various atmospheric conditions. The primary frequencies include L1 or the 1575.42 MHz for civilian use, L2 or the 1227.60 MHz for ionospheric correction and military applications. The L5 or the 1176.45 MHz, which is a more robust signal designed for safety of life application like aviation. Because of multiple satellites transmit on these same frequencies, ranging codes are used to provide each satellite with a unique identity through code division multiple access. These codes, such as the civilian or CA, course or acquisition, and the encrypted military, allow the receiver to calculate the precise time of flight by matching its internal code within the received signal. Superimposed on these codes is the navigation message, a low-bitrate data stream that provides the receiver with the necessary cargo to compute a position. This data includes the ephemeris, which give high accurate orbital parameters for the specific satellite, the almanac, which provide general status and approximate location for the entire constellation, and the clock correction to account for a minute drifts in the satellite's atomic clock. Together, these components allow the receiver to determine exact where a satellite is in space and how long the signal took to arrive, which is the foundation of the precise global positioning.
Error sources. Calculating an accurate of GNSS, that means Global Navigation Satellite System. That position requires overcoming several physical and technical error sources, primarily atmospheric interference, multipath errors, and clock biases. The atmospheric interference occurs as signals pass through the ionosphere, where charged particles slow down the radio waves, and the troposphere, where water vapor and pressure changes cause further refraction, and the multipath errors arise in environments with many reflective surfaces like cities or mountains, that causing the signal to bounce before the antenna and resulting in artificially long travel time. Finally, clock bias represents the timing discrepancy between the ultra-precise atomic clocks on the satellites and less expensive quartz clocks found in consumer receivers, while satellite drift is corrected via ground control updates. Receiver clock bias is resolved mathematically by requiring a minimum of 4 satellites to provide a synchronized three-dimensional position. Differential GPS or the DGPS and augmentation. Differential GPS represents a critical enhancement to standard satellite navigation, designed to mitigate the inherent errors caused by atmospheric interference and satellite clock biases. The system relies on a stationary reference station positioned at a precisely surveyed known location. By comparing its known coordinates with the signals received from the GPS constellation, the station can calculate the exact timing and positioning errors occurring in real time. These corrections are then transmitted to mobile or the rover receivers in the area, which apply the data to their own calculations to cancel out or the common mode errors. This collaborative approach dramatically improves spatial accuracy, enabling high precision application in fields such as autonomous farming, maritime navigation, and land surveying, where standard GPS tolerance will be insufficient.
I'll be discussing the theoretical background. The fundamental principle behind modern satellite-based positioning is the precise measurement of the time it takes for a signal to travel from a known location to a receiver. By utilizing the constancy of the speed light and the geometric properties of intersecting spheres, a receiver exact position can be determined in three-dimensional space. So this means the core principle of modern satellite-based in positioning is measuring the time signal that takes to travel from the satellites, which is known as location, to a receiver. Using the fixed speed of light and the geometry of intersecting spheres formed by signal travel, distance, and receiver, exact 3D position can be calculated. So we will proceed to practical application and operation. The practical application of global navigation satellite system is commercial aviation marks a fundamental transition from ground-based on sensor-dependent navigation to a highly flexible performance-based environment. So it means in commercial aviation, global navigation satellite system or GNSS drive a major shift from ground-based sensor-reliant navigation to a flexible performance-focused system. This also allows for more adaptable flight operation compared to traditional methods.
Standard and guidelines. The ICAO Performance-Based Navigation Framework represents a fundamental shift in global aviation, moving the industry away from rigid reliance on ground-based sensor signals towards a more flexible, capability-driven model. Under the traditional system, aircraft were tethered to the location of physical beacon like VOR or DME. In contrast, the PBN concept allows an aircraft to follow a highly accurate, predefined flight path by leveraging a combination of onboard systems such as GPS or inertial navigation to meet specific performance requirements. This transition optimizes airspace, reduces fuel consumption, and enhances safety by providing more predictable and efficient routing. The three pillars of PBN. To function effectively, the PBN framework integrates three interdependent components. Naval infrastructure. This is the backbone of the system. It refers to the physical hardware, whether ground-based (DME or VOR) or space-based (GNSS, GPS), that provides the raw positioning data the aircraft uses to locate itself in 3D space. Navigation specification. This acts as the rule book for a specific route or airspace. It defines the required technical performance, specifically in terms of accuracy, integrity, availability, and continuity. For example, a specification like RNP1 requires the aircraft to remain within 1 nautical mile on the certain line 95% of the time. Navigation application. This is the practical deployment. It is the result of applying a specific navigation specification to a defined route or procedure, such as an arrival or departure, within a specific NAVAID environment. The standard and guideline governing modern aviation navigation focuses heavily on the shift from sensor-based systems to provide-based requirements, as outlined in ICAO DOC 9613 for Subtopic 2. The core distinction between RNAV and RNP lies on monitoring and alerting. While both allow for flexible flight paths, RNP standards mandate that the aircraft system must monitor its own performance and alert the pilot if the navigation error exceeds a specific limit typically defined as the integrity limit. This is often visualized as a containment area where the aircraft must remain within a specific nautical mile distance from a center line for 95% of the flight time. Regarding subtopic 3, the RNP 0.3 specification provides a highly accurate standard, primarily utilized for rotorcraft operation and complex approach paces. The guideline dictates a literal accuracy of 0.3 nautical miles, which is essential for point-in-space procedure. These standards allow helicopters to navigate safely through dense urban environment or mountainous terrain by significantly reducing the required obstacle clearance areas. By adhering to this strict tolerance, operation can achieve lower descent altitude and more efficient routing in constraining airspace. Subtopic 4. The RNP tunnel concept is governed by the total system error model. The TSE is the statistical sum of the path-defined error, the flight technical error, and the navigation system error. Guidelines required the combination of these three errors must not exceed the specific RNP value under the normal operating conditions. Furthermore, the system must meet a high level of integrity, specifically a probability of no more than 1 times 10 raised to negative 7 per flight hour that the aircraft will exceed the defined containment limit without an onboard alert. This reduces mathematical framework and safe and reliable corridor for all phases of flight. Challenges and future trends. The vulnerability of GNSS to signal interference remain a critical hurdle for modern navigation, as the extremely low power of satellite signals make them easy to target for jamming and spoofing. To mitigate the threat and address the inherent problem of integration drift, where small sensors error accumulate over time, the industry is increasingly moving toward deep integration with inertial navigation systems. While GNSS provides high absolute accuracy, it is susceptible to outrage conversely. INS is autonomous and highly frequency, but drifts significantly without external correction. By fusing these technologies using advanced algorithms like extended Kalmar filter, the system can use GNSS to reset an INS error budget while the INS provide a continuous navigation solution during GNSS denied periods. Looking ahead, the trend is shifting toward all source positioning. This supplement GNSS and INS with visual odometry, LiDAR, and signal of opportunity, such as 5G or Starlink, to create a resilient positioning engine essential for the future autonomous vehicle and urban air mobility.